Hey everyone, and welcome. Today, we're putting on our detective hats and diving deep into the chemical world. We're going to be uncovering the secret identities of some of the most common yet powerful chemicals out there: acids, bases, and salts.
So let me ask you something right off the bat. What on earth could possibly connect the toothpaste you used this morning, an antacid you might take for heartburn, and the soil in a farmer's field? I know, it sounds totally random, right? But believe it or not, there's a fundamental chemical principle that links them all, and we're about to break it all down.
All right, to get to the bottom of this mystery, we first need to meet our main players, our main suspects, if you will. On one side, we have acids, and on the other, their chemical opposites, the alkalis. So here's the basic rundown of what makes them tick. At their very core, acids are substances that when you dissolve them in water release these little things called hydrogen ions, or H+. You can think of those H+ ions as their secret weapon, their active ingredient. Now, alkalis, which are just bases that happen to dissolve in water, they do pretty much the same thing, but they release hydroxide ions, OH-. And of course, there's the classic lab test you might remember. Acids turn blue litmus paper red, and alkalis do the opposite, turning red litmus blue.
Okay, but here's where it gets interesting. Do these chemicals always act this way? Are they always on? Or is there maybe a secret ingredient they need, a hidden switch that has to be flipped for them to reveal their true nature?
And here we see that secret ingredient in action. It's a really simple but powerful demonstration. If you take a solid, completely dry acid and just place it on a piece of dry litmus paper, absolutely nothing happens. Why? Well, because those H+ ions, their secret weapon, are locked up tight, stuck in a crystal. But the second you add a few drops of water, it's like a key unlocking a cage. The acid ionizes, those H+ ions are set free to roam, and boom, the litmus paper instantly turns red. So, the big takeaway here is water is the magic ingredient. No water, no acidic or alkaline powers.
Okay, so we know who our players are, and we know what it takes to activate them. But how do we measure their influence? I mean, how do we tell just how acidic or how alkaline something really is? How strong are they?
Well, for that, we turn to something you've probably heard of, the pH scale. The easiest way to think of it is like a power meter for chemical solutions, and it runs from 0 all the way to 14. Anything with a pH below 7 is considered acidic, and the lower the number, the more acidic it is. Anything above 7 is alkaline, and right there in the middle, at a perfect pH of 7, is neutral. Think pure water. It's all about measuring the concentration of those free-roaming H+ ions.
Now this is a really important point, and it's where a lot of people get mixed up. We often use the words strength and concentration interchangeably, but in chemistry, they mean two totally different things. Strength is all about how completely an acid breaks apart in water. Does it release all its H+ ions or just a few? Concentration, on the other hand, is just about how much of the stuff you've actually dissolved in the water. So you can totally have a dilute solution of a very strong acid.
And this chart makes that difference crystal clear. Take a look. We have two different acids, both at the exact same concentration. But look at the pH. The strong acid, hydrochloric acid, has a super low pH of 1. The weak one, ethanoic acid, is way up at 2.9. That is a massive difference in power. And it's all because that strong acid completely breaks apart, flooding the solution with H+ ions and tanking the pH. The weak acid, it just kind of reluctantly lets a few of its ions go.
All right, we know who they are. We know how powerful they are. So now for the fun part. Let's get into the action sequence. What actually happens when acids start interacting with other substances?
Let's walk through two classic telltale reactions you'd see in a lab. First up, if you add an acid to a metal carbonate, think something like chalk or marble, you get instant fizzing. That's a gas, carbon dioxide, and the surefire way to prove it is to bubble it through lime water and watch it turn cloudy. Second, if you drop a piece of a reactive metal, like zinc, into an acid, you also get fizzing, but this time it's a different gas, hydrogen. And you can prove that by collecting some and hearing that very distinct pop sound when you bring a lighted splint near it. But of all the reactions, there is one that stands out. It's the main event. It's what happens when an acid and an alkali finally come face to face. We call it neutralization.
And neutralization is pretty much exactly what it sounds like. It's the ultimate chemical balancing act. An acid and a base react, they completely cancel each other out, and what you're left with are two perfectly neutral substances, a salt and good old water.
But if you zoom all the way in, down to the ionic level, all of that drama boils down to this one super simple, really elegant interaction.
The hydrogen ion, H+, from the acid finds the hydroxide ion, OH-, from the alkali. They combine, and they form a stable, neutral water molecule. They've perfectly canceled each other out. That's it. That's the heart of all neutralization.
And this brings us right back to our original question. This whole neutralization thing isn't just happening in a lab. It's happening all around us every single day. That antacid tablet you take, it's just a base that's designed to neutralize the excess acid in your stomach. Your toothpaste is slightly alkaline to neutralize the acid that bacteria make on your teeth. And farmers? They add a base called slaked lime to their fields to neutralize soil that's gotten too acidic, which helps their crops grow better. It's literally chemistry in action, solving real-world problems.
So, we've talked a lot about water being one of the products of neutralization. It's a pretty big deal. But what about that other product? What exactly are these salts that get formed in the process?
Now, when a chemist says salt, they're not just talking about the stuff you sprinkle on your food. That's just one specific type. In chemistry, a salt is any ionic compound that's created when the hydrogen ion of an acid gets kicked out and replaced by a metal ion, like sodium or copper, or the ammonium ion. It's a huge and incredibly diverse family of compounds.
And this little table is basically a chemist's cheat sheet for predicting what will happen in a reaction. Some simple rules of thumb are incredibly useful. For instance, all nitrate salts will dissolve in water. No exceptions. It's a great rule to remember. For chlorides and sulfates, most of them dissolve, but there are a few very famous exceptions you have to watch out for. And carbonates? They're usually the opposite. Most of them don't dissolve. Knowing these basic rules lets you predict whether you're going to form a solid in your test tube or not.
Okay, we've covered the theory, we've seen the real-world applications, so now it's time to put it all together. It's time to put on your detective hat for real and use everything we've learned to solve a chemical mystery.
So imagine this. A small vial with an unknown white crystalline powder lands on your lab bench. You're told it's a salt, but that's it. Which one is it? What's inside? Where do you even begin? Well, you do what any good detective would do. You start looking for clues.
One of your first moves could be a simple heating test. See, when you heat many salts, they decompose, and they leave behind a metal oxide. And what's really cool is that the color of that leftover residue can give you a massive clue about the identity of the metal ion or cation inside. So for example, if the stuff you're left with is yellow when it's hot, but then turns white as it cools down, you can be pretty darn sure you're dealing with a zinc compound. It's a classic clue.
And these tests? These are how you confirm your suspicions and close the case. Once you have a lead from a test like heating, you can use a specific, targeted test to prove it beyond a shadow of a doubt. And these tests are often incredibly dramatic and visual. A single drop of the right chemical can produce a shocking blood-red solution if iron 3 is present, or a vibrant, bright yellow solid if you've got lead 2. These are the chemical fingerprints that solve the mystery.
So there we have it. We've gone from the simple definitions of acids and alkalis all the way to acting like a chemical detective and identifying an unknown substance. It just goes to show you that with a little bit of knowledge about the rules of the game, you can start to decode the chemical world that's all around us, which really makes you wonder, if you can figure out the secrets hidden inside a tiny salt crystal, what other mysteries are just out there, hiding in plain sight, waiting to be uncovered?